Right now, the world's smartest AI can, write a brilliant, complex software application in a matter of seconds. But it can't figure out how to click a basic checkout button on a retail website.
Yeah, which is kind of wild when you think about it.
It really is. And for a long time, we've just assumed that AI is naturally going to evolve from talking to us to, actually doing things for us. Because you don't just want an AI that can write a polite, perfectly formatted email to customer service. You want an AI that can log into the airline portal, navigate through the labyrinth of menus, click the right buttons, and actually rebook your canceled flight. You want an agent.
Right, and that is the crucial distinction we're facing today. We are trying to cross this massive chasm from generative AI, which simply outputs text or images based on patterns, to agentic AI.
Which takes action.
Exactly,
Yeah.
taking autonomous sequential actions inside a dynamic environment to achieve a specific goal.
But there has been this huge, almost invisible wall standing in the way of open source AI actually crossing that chasm. Because, we are all so completely obsessed with the models themselves, like how many billions of parameters they have, or how smart they score on standardized tests.
We completely ignore the infrastructure.
Right, we ignore this incredibly boring sounding bottleneck that is keeping these agents from actually learning how to do chores. And that bottleneck is the environment, the sandbox where they practice.
Which turns out to be everything.
So, our mission for this deep dive is to explore a foundational shift in how we build these AI agents. We are looking at a state-of-the-art research paper from Microsoft Research, Columbia University, and UIUC. And they've introduced a new open source framework called Orchard, and it completely changes the game.
Okay, let's unpack this. Why is a sandbox such a massive, prohibitive problem in the first place? Well, to understand the sheer scale of the problem Orchard solves, you really have to look at the fundamental difference in how an AI learns to take action. When you train a standard chatbot, you are just feeding it static text, right?
Just reading the internet.
Yeah. It reads the internet, learns grammar,
Yeah.
predicts the next word. It's a completely passive observer. But to train an AI agent to, say, fix a software bug, it can't just read static code.
It has to do stuff.
Right. It needs to actively try things and see what happens. It needs a fully functional simulated computer to clone a repository, install dependencies, run a test suite, observe the error logs, edit the file, and then run the test again.
So it's kind of like the difference between reading a textbook about how a combustion engine works and actually getting under the hood of a car with a wrench and turning bolts to see what happens.
That captures the dynamic perfectly.
Hmm.
And to get good at turning those bolts, an AI needs to do it thousands, if not millions of times concurrently.
Oh, wow.
Millions of times. Yeah, which requires infrastructure on a scale that is just hard to fathom. You have to spin up thousands of isolated, secure, simulated computers, these sandboxes, all at the exact same time.
So how is anyone doing this right now?
Well, currently, the open research community really only faces two very restrictive options to achieve this. Option one is using proprietary managed services like E2B or Daytona.
Okay, so just paying a company to host it for you.
Exactly. They're essentially companies that host the sandboxes.
Yeah.
And they're incredibly easy to use, but the financial toll is astronomical. The paper notes that running just 128 parallel sandboxes for a week and a half costs over $7,000.
Over $7,000 for a week and a half, which means if you are a trillion-dollar tech monopoly, that's, pocket change.
Right.
But if you are an independent academic researcher or like a small open source startup trying to build the next great model, you are priced out of the game before you even start.
Precisely the issue. And option two really isn't much better. Option two is building these vertically integrated training stacks.
What does that mean exactly?
So these are rigid systems where the sandbox environment is tightly hard-coded into the specific task or the specific training loop the researcher is using.
It's like if you wanted to teach 1 million people how to drive, but instead of just having them use a fleet of standard rental cars on a normal highway, you were forced to build a brand new custom-made vehicle and construct a unique custom-paved racetrack for every single student every single time they wanted to practice.
Yeah, the logistics and the cost of building custom infrastructure every time would bankrupt you immediately.
It's just financially impossible.
It is. And what's fascinating here is that logistical nightmare is exactly what led the researchers to their core realization. The environment isn't just an IT problem or a web hosting issue. It is the fundamental bottleneck dictating whether training recipes and data sets can actually be reused by the broader community.
Because they're locked down.
Exactly. If your sandbox is locked down behind an expensive paywall, or hard-coded into a rigid script, no one else can reproduce your work or adapt your agent to a new task.
So if the current sandboxes are either way too expensive or way too rigid, how does the Orchard framework break that trade-off? Because when I was reading the paper, they introduced this core solution called Orchard Env.
Yeah, the environment layer.
Right, and they describe it as a thin Kubernetes native environment service that acts as a standalone boundary. It supposedly doesn't care what agent you use, what training method you use, or what the specific task is. But wait, I have to push back a little here.
Okay, go ahead.
Kubernetes isn't exactly a new technology. I mean, it's been the industry standard for managing cloud applications for years. Why is using Kubernetes suddenly a game changer for AI agents?
Well, it is entirely true that Kubernetes is standard infrastructure,
Yeah.
but it is how Orchard manipulates that standard infrastructure that makes the difference here. They engineered two massive technical breakthroughs to make this work for AI agents at massive scale.
Okay, what's the first one?
The first breakthrough is what they call runtime agent injection. Normally, if you want an AI to practice in a specific environment, say you want it to fix a bug in an outdated version of a Python repository, you have to build a custom Docker image.
Okay, for those of us who aren't DevOps engineers, what exactly is a Docker image in this context?
Good question. Think of a Docker image as a frozen, meticulously packed snapshot of a computer.
Like a save state in a video game.
Yeah, kind of.
Uh-oh.
It contains the operating system, the specific Python repository, all the files, and crucially, the custom communication software needed to let your specific AI talk to that environment.
Right.
And building these custom frozen snapshots for every single task takes an immense amount of time and uses huge amounts of server storage.
Ah, so you're building that custom car for every driver all over again.
You are. And Orchard bypasses that entire heavy process. Instead of rebuilding those frozen snapshots, Orchard takes whatever generic raw task image you provide. Doesn't matter what it is. And at the exact millisecond that sandbox starts up, Orchard automatically injects a tiny, lightweight execution agent right into it.
Just on the fly.
Just on the fly.
Yeah.
This execution agent is just a tiny piece of software that handles the communication. You never modify the heavy images at all. You just inject the communication layer at startup.
That is incredibly elegant. It just slides the walkie-talkie under the door right as the room is built so the AI can start giving commands immediately without needing a custom-built room.
Exactly.
Okay, so slipping the agent in on the fly solves the setup time. But once the agent is inside the room, it still has to send hundreds of complex commands back and forth to practice. Doesn't that create a massive traffic jam on the network when you have thousands of these sandboxes running?
That exact network traffic jam is what the second breakthrough addresses. It is called direct pod IP routing.
Direct pod IP routing. Okay.
So in a standard Kubernetes setup, when you want to execute a command inside a sandbox, that command request has to travel through a central hub called the Kubernetes API server or the control plane.
Like a central dispatcher.
Yes. This control plane is the central brain of the cluster. It checks permissions, authenticates the user, sets up the network connections. It is highly secure, but it adds a tiny bit of latency to every single request.
Which normally wouldn't matter.
Right, a human wouldn't notice it, but
Yeah.
when an AI is practicing, it might issue hundreds of shell commands a second. Going through that central toll booth every single time brings the entire system to a crawl.
The control plane just gets totally overwhelmed.
It does. So Orchard fundamentally splits the traffic.
Yeah.
The orchestrator still uses that central API toll booth for administrative tasks, like creating or deleting the sandboxes. But once the sandbox is actively running, the AI sends its execution commands directly to the IP address of that specific sandbox.
It totally bypasses the central API server for the actual task execution.
Exactly. It routes directly to the pod.
And looking at the hard numbers from the paper, the impact of bypassing that toll booth is staggering. Because of that direct routing, the execution latency drops to a blistering 0.28 seconds.
It's incredibly fast.
Yeah. And when the researchers ran a stress test trying to spin up and actively use 1,000 parallel sandboxes at the exact same time, it maintained a 100% success rate. Nothing crashed, no network timeouts.
Which is unheard of for that kind of scale.
Right, and because this entire framework is built on standard Kubernetes, You can run it on what cloud providers call spot instances.
Yes, the cheap servers.
Exactly, which is basically renting leftover, unused server space from Amazon or Google at a massive discount. That combined efficiency drives the cost down to 10 times cheaper than those managed alternatives like Daytona or E2B.
10 times cheaper.
It takes a $7,000 training run and turns it into a $600 training run.
Which fundamentally shifts who gets to participate in this research.
Yeah.
It makes large-scale agent training accessible to university labs and small developers.
So we've essentially built a hyper-efficient, lightning-fast playground. But a playground is useless if the AI doesn't know what games to play. How did the researchers actually use this infrastructure to make a model smarter at, say, software engineering?
Well, let's look at their first practical recipe, Orchard SWE.
SWE being software engineering.
Right. This recipe reveals a profound shift in training philosophy. They wanted to teach an open-source model how to autonomously fix real-world GitHub issues.
Okay.
So they began by distilling knowledge from massive, state-of-the-art teacher models, specifically Qwen 3.5, which has almost 400 billion parameters, and Minimax M2.5.
These are giant models.
Huge. And they unleashed these massive teacher models into the Orchard sandboxes to try and solve thousands of complex coding problems. As the teachers worked, the system recorded everything.
Like every single keystroke.
Yes. They collected 107,000 trajectories. And a trajectory is simply the step-by-step digital footprint of everything the AI did. The terminal commands it ran, the files it opened, the code it searched, the text it edited.
So they're essentially building a massive textbook of practical examples for the smaller model to study.
Right. And that process is known as supervised fine-tuning, or SFT. But the Orchard researchers identified a critical flaw in how standard SFT is usually done.
What's the flaw?
Normally, researchers only keep the trajectories where the giant teacher models successfully fix the bug. If the teachers spend 50 steps trying to fix a bug and ultimately failed the test suite, researchers just throw that entire trajectory in the trash.
They just discard it.
Yeah, they assume you should only train on pure success.
But the Orchard researchers didn't do that. Here's where it gets really fascinating. They kept the failures.
They did.
They trained their new model using both the resolved, successful trajectories and the unresolved, failed ones, which makes total sense when you map it to human learning. Think about a math teacher giving a student a really difficult calculus exam.
Okay.
Even if the final answer at the bottom of the page is completely wrong, the steps the student took to explore the problem, like setting up the initial equation, correctly isolating the variable, applying the right formula, those initial steps were incredibly valuable.
Absolutely.
A good teacher doesn't just throw the whole test in the trash, they give partial credit. They reward the correct logical thinking up to the exact point where the arithmetic mistake happened.
And that partial credit concept is exactly what they engineered here. The paper calls this credit assignment SFT.
Okay, credit assignment SFT.
But the technical challenge is immense.
Right.
Because how do you mathematically give an AI partial credit for a failed attempt?
Yeah, the sandbox environment doesn't have nuance. It just runs the final test suite and says fail.
Exactly. It doesn't tell the AI where it went wrong in a 50-step process.
Right, so how do they actually grade the digital scratchpad?
Well, they utilize a technique called retrospective value estimation. They took the massive teacher model, and they showed it the entire failed trajectory from step 1 to step 50, along with the final failed test results.
Okay.
They essentially told the teacher, look at this failure and analyze it backward. They asked the model to map out the mathematical probability of success at every single step of the process, given that it already knows the final outcome is a failure.
Oh, wow. So they are mapping the exact moment the train went off the tracks.
They are. And what emerges from this backward analysis is what they call an inverted U probability curve.
So imagine a graph.
Right. At step 1, the probability of success is at a baseline. As the AI successfully navigates the repository, runs a search command, correctly identifies the file containing the bug, the probability of success rises. The AI is doing the right things.
That is the upward slope of the U.
Yes.
Yeah.
But then, at, say, step 15, it makes a critical logical error when editing the code.
Yeah.
The probability of success plummets instantly.
And it stays flat at 0 until the end of the trajectory because the agent is doomed and just doesn't know it yet?
Precisely. So the researchers mathematically isolate that upward slope. They call them rise segments. These are the specific contiguous steps where the AI was making positive, productive progress exploring the environment before it ruined everything.
Oh, I see.
They extract those rise segments and feed only those productive steps into the training data for the smaller model. They are teaching the smaller model how to effectively explore a new codebase using the pure signal of good exploration extracted from a noisy failure.
So they learn the good exploration paths from the failures, but is that it? Just studying the partial credit?
Well, that is just the supervised learning phase. The next step is where the speed of the orchard sandbox becomes critical. They move to reinforcement learning.
Where it practices on its own.
Right, where the model just practices on its own and gets rewarded for passing tests. But they use a specific technique here called balanced adaptive rollout, or BIR. In standard reinforcement learning, a model might waste thousands of hours trying to solve an impossibly hard bug, or over-practicing on a bug it already knows how to fix.
It gets stuck in a rut.
Yes, so BI monitors the AI's progress in real time. If the AI is exploring a problem and making steady progress, like passing more tests, getting closer to a solution, BIR dynamically allocates more computational resources to let it keep trying.
But if it gets stuck,
If the AI hits a wall and stops making progress, BIR immediately cuts the attempt short and resets the sandbox. It perfectly balances the exploration, ensuring the model spends its compute time on the most valuable learning experiences.
and when you combine that partial credit training with the ultra-efficient balanced adaptive rollout in these super fast sandboxes, the results are stunning. I mean, the researchers took a relatively small model, a 30 billion parameter model, which is tiny compared to the big proprietary ones, and they reached a 67.5% resolution rate on the SW Bench verified test.
Which is incredible for that size.
It sets a brand new state-of-the-art for open source models in that weight class. It is going toe-to-toe with massive 500 billion parameter behemoths simply because it was trained more efficiently.
Yeah, better training beats size.
But software engineering is a very specific domain, though.
Yeah.
What happens when you drop this agent into an everyday scenario? Can this framework teach an AI to do the things you and I do every day, like booking a flight or managing a calendar?
It absolutely can. The researchers introduced 2 more training recipes to prove that Orchard is a truly generic agnostic framework, Orchard GUI and Orchard Claw.
GUI being graphical user interface, so teaching the AI to use a standard web browser.
Right.
But how does an AI even see a browser to click on it?
For Orchard GUI, they use a vision language model, or VLM. This model doesn't just read the hidden HTML code of a website. It actually looks at a visual screenshot of the browser.
Like it actually sees the screen.
Yeah. It is trained to map the visual elements it sees, like a checkout button or a search bar, to specific X and Y coordinates on the screen, allowing it to output a command that moves the mouse and clicks exactly where a human would.
The GUI experiment is where I think the most shocking detail in the entire paper is hiding. It is a real David versus Goliath situation. Because for Orchard GUI, they didn't use a 30 billion parameter model. They used a tiny 4 billion parameter vision language model.
Which is tiny.
To put that in perspective for you listening, 4 billion parameters is small enough to run locally on a modern laptop, and they trained it on a minuscule data set, just 400 trajectories and about 2,200 open-ended tasks.
By modern AI standards, that is a microscopic amount of data.
And yet, this tiny 4B model, practicing inside the generic Orchard sandbox, achieved a 68.4% average success rate across major web navigation benchmarks. It is successfully navigating sites, clicking dynamic menus, and solving multi-step web problems.
And if we connect this to the bigger picture, the implications of that specific number are profound, because that 4B model didn't just perform well for its tiny size. It actually outperformed its own 235 billion parameter teacher model.
Which is crazy. How does a tiny model beat the very teacher it learned from? That defies the logic of just copying a textbook.
It comes back to the power of environment-grounded reinforcement learning. When the tiny model is placed in the Orchard sandbox, it isn't just mimicking the text its teacher wrote. It is actually interacting with a real responsive web browser.
It's doing it for real.
Right. If it clicks a menu and a drop-down appears, it sees the consequence of its action. If it clicks the wrong button and gets an error page, it gets penalized. By physically interacting with the environment, it learns the underlying physics and logic of user interfaces. It learns concepts rather than just memorizing brittle scripts.
Learning by interacting is exponentially more powerful than learning by reading. It's like you can memorize an entire encyclopedia on the fluid dynamics of surfing, but the person who actually gets in the water every single day and feels the wave is going to be a better surfer, even if they haven't read a single page.
Exactly. The environment teaches you nuances the text simply cannot convey.
And the results from the final recipe, Orchard Claw, reinforce this conceptual learning, right?
They do. Orchard Claw trains a personal assistant agent to handle productivity workflows, like checking email or managing a calendar. They trained this assistant on a tiny data set of synthetic tasks, and it hit nearly a 60% success rate right out of the gate.
Impressive.
But the real proof of conceptual learning came when they tested its adaptability. When they swapped out the interface, it was using for a slightly improved version during the testing phase, an interface it had never seen during training. Its success rate jumped to nearly 74%.
Wait, it went up. It didn't break because a button moved. It adapted.
Because it practiced in a flexible, responsive sandbox, it learned the fundamental goal of managing a calendar, regardless of where the specific buttons were placed.
So to bring this all home for you listening, why should you care about Orchard, Kubernetes, and direct IP routing? For a very long time, it really looked like the future of agentic AIs that actually take action in the real world was going to be entirely locked up by the richest tech monopolies.
Because of the cost.
Yeah, they were the only organizations on Earth who could afford the massive server farms and the astronomical costs required to simulate the thousands of environments needed for an AI to practice. They were the only ones who could afford to build 1 million custom cars and 1 million custom racetracks.
And that kind of extreme centralization of capability is dangerous. It stifles open research, it limits innovation, and it dictates who controls the autonomous systems of the future.
But Orchard democratizes this entire process. It proves that you do not need a billion-dollar supercomputer to train a highly capable agent. By engineering a clever, thin, extremely fast, and incredibly cheap environment layer, by just slipping the walkie-talkie into the room at the last second and bypassing the central toll booth, open source AI can catch up using a fraction of the compute power.
A tiny fraction.
A tiny 4 billion parameter model can take on a 200 billion parameter giant simply because it finally had a better, cheaper place to practice and learn from its mistakes.
It levels the playing field. The simulated environment is the fundamental substrate of learning for these agents, and Orchard just made that substrate accessible to the entire open source community.
Which leaves us with a really provocative thought to mull over. The Orchard framework is entirely agnostic. It doesn't care if the sandbox is a web browser or a coding terminal. So, if we have now perfected a framework where open source AI can cheaply and rapidly learn from millions of simulated failures in a generic software sandbox, what happens when we start plugging this open source infrastructure into physical simulations?
Oh, it's a huge question.
Right. Could the next major breakthrough be an open source AI teaching itself to discover new lightweight materials for spacecraft, or fold complex proteins, or design life-saving new drugs by failing millions of times a second in a virtual sandboxed chemistry lab?
The possibilities are endless.
If the invisible ceiling holding AI back was just the cost of the sandbox and we just shattered that ceiling, AI isn't just going to learn how to book our flights. It's going to learn how to manipulate the physical fabric of the world, all because we finally gave it a cheap, fast place to practice.